Hi again, just reviewing week 4's outputs for you. We did two things. We looked at correlations and ways of measuring correlations, that's the association between pairs of variables, and also ways of assessing the normality of the distributions of the values in a sample. And rather than using QQ-plot, we've got the option of using one of various tests, and this is the Shapiro-Wilks test, is one of them for testing for normality. This is two examples that have been applied to two of the variables in the dataset, comp memo mean and comp whatever it is, spec mem mean, and we can see that the W statistic, the Shapiro-Wilks statistic, is large, and the probability of getting a value as large as that under the assumption of the null hypothesis is small. Okay, here's an example of our correlation plot. Okay, on two of the corresponding sets of data. These two, in fact. Student comment: this computation suggests the data on these two variables is relatively normally distributed. There are obvious deviations, especially near the 6 measurement on the comp memo mean measurement. So what's wrong with this? Well, it's a confusion between testing for normality, which in these cases apply to a single sample, and making conclusions about the relationships between samples. So we were doing two different things. Okay, in order to decide whether or not you can use Pearman's correlation, you have to make sure that your samples are normally distributed, and if they're not, then you have to use one of the other types of correlation measure. And so therefore, before you can do this, you have to do the normality test on the individual samples. Okay. Here's another one here. Someone has applied the Shapiro-Wilks test. The probability values for both the x-axis and the y-axis are above 0. Well, first thing is they should refer to the variables here, and the probability values, of course, the Shapiro-Wilks test only provides a single probability, and I can only think that they're talking about the location along these axes of most of the points. It's not clear at all, so someone's really misunderstood that. Here's some more about the Shapiro-Wilks test, the test for normality on one sample. As the data is significant, the mean is not normally distributed, so we can reject the null hypothesis and accept the claim that pregnant women's mean is very similar to it. Right, that's whatever it is, claim 1. As the data, so as remember, this is a test for normality. Okay. And here the claim that they're talking about is a comparison between pairs of measures. So this is saying that by applying a normal distribution test, we can say something about the comparison between the means of two different variables. Not so. Here's someone else. As we can see in the table below of the Shapiro-Wilks test, the probability is this. Therefore, with a probability of less than 0.05, it means that the population is normally distributed, and the null hypothesis of the difference between populations is rejected. This, that, and the other. Right? Two things going on here. Shapiro-Wilks test. Remember, the null hypothesis for these things is that things are normal. Right? So in this case, if the test works out okay, so if the thing is normal, which is what it's designed to test for, then it shouldn't be significantly different from normal. Okay, in this case you're getting a very small probability of having a test result, that is that W statistic that's calculated by the Shapiro-Wilks test, of such a size that would only occur with a frequency of 4 times in, let me see, where's my pointer gone, 4 times in 10,000. Okay, very unlikely. So it doesn't mean that the population is normally distributed, it means the opposite. Okay, and anyways, you're not testing about the difference between populations. Okay, that's the difference test is something else altogether. We're looking at the correlation, the association between variables. The kind of difference test we've done before would be, for instance, the box plots, where we can look at the where the medians are, and if we use the notched box plots, if the notches don't overlap, that's an indication that the medians are significantly different. Okay, so Shapiro-Wilks test is a test of normality, not a measure of correlation, and its null hypothesis is that data is normally distributed, and if you get a significant result, okay, it doesn't mean you found what you wanted to find, it means that it's not normally distributed. The end, says Olivia. Correlations, okay, so it's a scatter plot with a line through it, and this isn't a test of normality, it's simply plotting pairs of values for individual participants, okay, for their scores on two different measures. So each one of these dots is a single person, and they've both got a score for comp memo mean and a score for spec10 mean. Okay, it's the third week of saying this. Yes, well, I can't remember, but what it's doing, it's giving an indication between the relationship between the two variables and the strength of the relationship. The more clustered this is along some kind of a curve, the more closely related things are. And if they're just all over the place with no sort of sense of order to them, then they're probably not related. Okay, this particular plot gives you at the bottom corner here the Pearson's correlation. In this case, if there was no correlation, this would be 0. The most this can be is +1 or -1 if the line is going in the opposite direction from the top left to the bottom right. If our samples turn out, either one of them or both of them, to be not normal, right, and we can't adjust them to normal by removing one or two outliers, then we have to use a non-parametric measure of association, like Spearman's rank order correlation, and sometimes called rho, and it gives us the strength of relationship between two variables. And again, like Pearson's correlation, it varies between plus and -1, and indicates in the same way as the Pearson correlation. It's the same kind of measure as Pearson correlation. And in terms of its outcome, okay, it gives you the strength of rho, and it also gives you whether or not the correlation is significant or not. And in this case, if p is less than 0.05, it means that the variable, sorry about that, is going to be significant, because the null assumption is that they're not related. So if the test doesn't produce an abnormal result, meaning one that's unlikely with a small p-value, then both of them are not going to be related. Okay, so in this case we're looking for an association to be indicated by a small p-value. When you report them, you've got to describe all your details, the p-values, the r value, the rho value, which way it's going, whether it's increasing or decreasing, and then say what it means. Okay, here's someone who said, here the probability of Spearman's correlation is this, very small number, which represents p is less than 0.05, correct. Therefore the null hypothesis is rejected, yes, and again the results are statistically significant, but hasn't said what we can conclude from those. So you have to go on to say, and this means that, our interpretation is, and so on. So final interpretation, be specific. Should, however, be cautious in drawing firm conclusions from this study, as there's a case to be made for arguing the variables are not independent of each other. Okay, so that's a good extra piece of observation and specific interpretation. Next one, when a collective group or sample is used in observation, can raise issues such as if one does something, the rest will follow. So this is a methodological point, but here no point making very general comments. It could be talking about a different study. Okay, so although this is true about correlation issues in general and the design of correlational observational studies, true, in this case we're looking for your interpretation of the outcomes of a particular analysis. Okay, and they've made these assertions without providing any evidence in terms of further details. Okay, that's all for this week.